Thank you so much, Kelvin, for the intro. And thank you, Median, for organizing this very nice conference. So just to introduce myself, if you don't know me yet. So my name is Sun Ho. So I'm just starting a tenure track position at KTH Mathematics this month, actually. And today I'm going to tell you about gated RNNs with weighted time delay feedback mechanism. So this is based on joint work with Ben Erickson and Michael Mahoney. So sequential data are everywhere. And more people are interested in how to model and learn this data. Typically, this data, they can be very long. So these sequences are very long, and they find many applications, such as in speech recognition, in videos captioning, even in image classifications, where you could think of the pixels, you could arrange a pixel from the image, right, in a sequence, and then you can try to learn the sequence that way. So obviously here we're interested in the long-range modeling capability of RNNs. Which is the topic of today's talk. So what is RNN, right, to begin with? So I'm sure you guys have heard about RNNs a lot in this conference, but basically they are brain-inspired models that people use in machine learning and also use as a model to study some neuroscience problem. They are essentially networks of neurons with feedback connections. And they're especially designed to process sequences. In particular, they can use a hidden state, right, to encode the memory to process this sequence. And it has been shown that they are universal approximators of dynamical systems. So here is a schematic of what a typical RNN looks like. So we have an input sequence, right? So X, X1, X2, X3. So things of the 1, 2, 3 as time, right? Time 1, time 2, time 3. And at each time, right, you feed the input Xi to the hidden state, okay? And then you apply some activation functions, and then you get output by doing some more transformations. You get Yi for each time. So you do this for all the time. So this is very different from the usual feed-forward network where we don't have this type of structure. There's no time, right, in the input data. So let's focus on the supervised learning framework for RNNs. So this is our setup. So we have data, training data. They are labeled. They come in pairs. So X is the input sequence. C denotes the label. And so mathematically, RNNs could be written as following. So this is a hidden out-there equations for the hidden state of RNN. So H here is what people call hidden state, right? And at each time t, right, we are going to feed in the input xt, and then there will be a nonlinear activation functions a that depends on both h and x at that time, and typically a is nonlinear. And then for the output y, you apply transformations g, right, to h of t. And typically g, people just simply take it to be linear transformations. Okay. So the simplest example of nonlinear activations would be just hyperbolic tangent. Okay. So there are many different variants of RNNs, right? So we have already seen many different versions in this conference. So early in the first day of this workshop, we see eco-state network, reservoir computers. And then, of course, practitioners are more familiar with the famous LSTM and GRU architecture. And then more recently, there are like a dynamical system inspired framework and design of RNNs. And more lately, there are state space models, which have shown remarkable performance for long-range modeling. I will talk a bit about SSM state space models a bit. Okay, here in the model, there are parameters data, and we are going to basically use empirical risk minimization framework, right, to learn the parameters, minimizing certain given loss assumptions, right? Okay, so now, the questions?
you're reading out only the last state, right?
Sorry, I have to go back. Oh.
So you're reading out the last one.
Oh, yeah, sure. I mean, like, actually, the output, you could actually define y for t from 0 to t minus 1, not necessarily at the capital T. But here, I was just thinking about classification problem, where you use the, the last, last time to do the classifications. Good point.
The notion of like memory and dynamics, that's not really important in the regression problem, right?
Yeah, the dynamic is mostly concerned about the dynamics of the hidden states, because you can think of the outdated equations of this equation as dynamical systems, discrete time dynamical system. So it's more about the dynamics of this hidden state, and in particular the stability of this system, because when we train them, typically using gradient descent, right, there will be some issues that I will talk about later, like vanishing and exploding gradient problem, especially if you have very long sequences. When you do back propagation through time, right, you need to be able to mitigate this type of problems. So that I will talk about later. Yep. Okay. So now the whole framework is that the whole idea is that we're going to start from a continuous time framework, right? So just now we look at discrete time versions of the equations. So the idea is that why don't we start from a continuous time differential equations, right? Simplest would be just like this non-autonomous ODE here, and and then the right hand side of this ODE depends on some parameter theta that we want to learn. And again, typical choice for the nonlinear functions f here would be just hyperbolic tangent. And then here, there are w, u, and b, which are the parameters to be learned. And why we do this, there are several advantages of considering continuous time formulation. One, here we go. So there are three views, point of views to think about this. So from design point of view, right? If we have continuous time system, right, we could basically try to use different numerical schemes to design different recurrent architectures. So give us some principle when we design the RNN. And from modeling point of view, in some cases, the input data themselves they are coming from underlying continuous time dynamical systems. So it seems natural to have architectures which is also continuous in time. And lastly, from analysis point of view, we have a lot of tools and techniques that we can borrow from continuous time theory. So these are the advantages of continuous time framework. And so just now I show you ODE. The focus of today's talk is how can we make use of delay differential equations to design improved versions of RMs. Okay, so there's some background materials here which I will go through rather quickly. So what are delay differential equations? So in ODE, the right-hand side of equations depends only on the hidden state at current time t. But in delay equations, it could also depend explicitly on the hidden state at time t minus tau, right? Where tau is the time lag. So here we have to be a bit careful here because in order to solve these equations, we have to specify initial functions, right? And then it is more useful to view these solutions as mapping of functions from functions to function into functions. And so this is what I'm just talking about. And in fact, there are functional differential equations, right? Living on some Banach space of continuous functions. And generally, they are infinite dimensional systems. So this is very different from ODEs that we just look at. So the starting point is the following continuous time delay differential equations. And now we are going to pick parameterizations, right, for the right-hand side. So a naive way to do it would be just simply like this in equation 2, where we have a damping term, right, negative h of t, and then there's a non-linear term, right, sigma of that depends on the hidden state at time t and also hidden state at time t minus tau, as well as the input x. Okay, so this is a very naive way to how we would design it. To better represent the number of time scales, right? We find that it's useful to consider time wrapping functions C, and we are going to model this the derivative of C in fact with respect to time with a neural network. So we can think of this as like some sort of gating function. Okay. C. Okay. So this is what we have, and then sorry, I'll go back. Yeah. Okay. So this is what we have. And so we have continuous time formulations of this, and now we're going to discretize this. The simplest scheme that you could think of is this explicit forward Euler scheme. So when you do this, and if here we just choose a step size to be 1, but in principle, you could use any delta t, right? For example, it could be useful for handling irregularly sampled data, but here we just pick delta t to be 1, and then we get 7. So these are the update equations for the hidden state. And see on so there's a gating functions, right, g of n, and then the second term on the right-hand side, there's a non-linear function sigma that depends on the hidden state at current iterations h of n, and also hidden state that depends on delay hidden state h of l. Okay. In fact, we are going to make the model a bit more expressive by considering a mixture of standard recurrent unit and delay recurrent unit. So we are going to replace the sigma that we saw earlier by a sum of 2 components, right? Un is just a standard recurrent unit like hyperbolic tangent of Hn and Xn, and then the second component would be the delay term, right? And then we are going to also consider functions A of m to weight the importance of the delay terms, component-wise. Okay, so this will make the whole model more expressive. Okay, so just to recap, right? So what we introduced here, right, is a model that consists of 3 main components. Okay, so there's a instantaneous dynamics part, which is the standard recurrent unit, and then there's a time delay component, right? And then there's also weighting functions that weight how important these delay terms are. Okay, and we are going to call these architectures tau GRU. Okay, so there are continuous time version, there are discrete time version, but we are going to focus on discrete time version mainly. So here is the whole formulation at one glance for you. Okay, so let's see what I will say here. So this is basically what I was saying just now. Okay, so now one can show that the continuous time tau GRU has a unique solutions. So this basically just borrowing classical result from delay differential equations. And this maybe it's not too important for this talk, but yeah, you can show some result like for assistant uniqueness, just to make sure that the things that we're considering here are okay. And so the more important thing here is, so what is the role of the delay term, right? So why are we using delay differential equations, right? So to understand this, we have to see how gradients are computed using backpropagations through time. Okay, so there are this BPTT, backpropagation through time, right? It involves 2 stages of unfolding a network in time and then backpropagating the training error, right, through the unfolded network. So when our architectures are unfolded in time, right? The intuition is that, so why these delays terms are useful is that these delays terms will act as some sort of like jump ahead connection. So this is what we call a buffer they will provide shorter path for propagating gradient informations. And to see how this what this means, let's just consider loss functions, just a mean square loss functions, and see how we compute gradient Okay. So basically, we use chain rule, right, to compute the gradient of loss with respect to the parameter, and we see that there are in 16 there are products of gradients like this. So these partial gradients, right, they appear in 16. They basically measure, right, the contributions to the hidden state gradient at each step m, right, due to the input informations at some step k. Okay. And this gradient behave like, say for some constant gamma gradient 0, behave like gamma to the power n minus k. Okay? So we see that if gamma is bigger than 1, right, then this gradient will grow exponentially. So for very long sequences, which is usually the case here, then this will explode, right? And if gamma is less than 1, there's also a problem of vanishing gradient problem, right? So I think our focus here is more on the vanishing gradient part, right? So how this additional delay terms could help with mitigating this vanishing gradient problem. So to understand, So to understand this, how delay terms could help with solving or mitigating this vanishing gradient problem, let's consider a very simple setting, right? Just a linear time delay RMM, and see how the gradients are computed, right? And then maybe we can get something out of it. So let's consider equation 17. So we see that there's a term bhm minus m, right? So there's a delay hidden state hm minus m there, and we want to see how they will appear in the gradient when we compute them. So let's just assume that everything is nice, right? A and B commute, but you could also do this for the case when they are non-commuting, but here I just want to simplify things. Then you can compute the derivative of hm plus 1 respect to input, say, ui, right? And then you can find this. So without the delay term, right? So if b equals 0, then the highlighted blue terms here, they will be vanishing, okay? But with b not equal to 0, then we have these extra terms in this color blue here. So what this means is that the addition of this delay term, right, they dampen the exponential decay by basically having these additional terms that perturb the gradients of a hidden state with respect to the input. So this help with lessening the vanishing gradient problem. Okay, so this is like this is useful to see how having a delay term help. You could also derive gradient bounds for our architectures, tau GRU, which is slightly more complicated, but yeah, you could get similar result. And again, if there's no delay term, then the blue terms there, they will be gone, right? And if there are delays, then they will be there. And the idea is the same, right? These additional terms will help with lessening the vanishing gradient problem. Okay. So let's see how effective are tau GRU in experiments, right? So the first benchmark task is what we call sequential image classifications. So we're going to consider, in fact, 4 different tasks. So first one is sequential amnes. So basically, you, again, like from the first slide, you have images. So this time is image from amnes. You are going to take the pixels and then arrange them in sequence, right? So this is what people call sequential amnes. And then there's a more challenging task of permuted amnes, where you permute the order of the pixels. And then there's sequential C-10 and noise padded C-10, which is much more challenging. So these are the results, right? When comparing the performance test accuracies of tau GRU when compared to the other state-of-the-art recurrent neural networks. Okay, so mainly in the more recent years, so we can see that our architectures is very effective in this task. And not only that, our architecture also they are able to converge faster during training when compared to other RNNs. So faster conversion and improved test accuracy for this task. So now ablation. So there are three main components, right? So why we need all of them, right? So obviously we play around with the architectures a bit, and we find that it's essential to have all three components. So first, the gating functions, which is needed to mitigate the exploding gradient problem, and then we also need both the standard recurrent unit and also the delay recurrent unit. So remember, we're considering a mixture of these two different units, and we found that we actually need both of them to achieve like optimal performance. And let's see, and then also we can also try to understand how we should pick, right, the value of tau, right. So obviously there's a sweet spot of tau that will allow you to achieve peak performance for certain tasks, right, for tasks that we consider. And also why we need these weighting functions, right? So without this, we found that they are not able to achieve better performance. So we also need to have these weighting functions to weigh the importance of these delay terms, okay? So gating, delay term, and the weighting functions. So all these are essential to good performance. So there are also other experiments that we consider, so such as sentiment analysis, human activity recognitions, and then when we compare the performance of tau GRU with other RNMs, we also find that so the performance is pretty good. And so how about learning nonlinear dynamics, right? So we consider a task of learning this climate model. So this is actually a delay differential equations for modeling ENSO. And when compared to other architectures, we also find that tau GRU perform very well. Okay. And similarly, we could do the same thing for McKee glass dynamics. So also we found similar results. So tau GRU is the best among the other among the RNN architectures that we consider. Okay, so now I have time. I think maybe I will just mention a bit SSMs. So state space models, which are nowadays are more popular because they have been shown to achieve remarkable performance for modeling really long sequences. And so why I'm talking about this? Because the thing is, when we submit this paper to review, right, and then people will be complaining why how would our architectures compare to more recent architectures? So here I'm just making some remark on this, just in case if you know what SSM are. So very briefly, so SSM are basically the key component SSM are linear RNMs, and so it involves choosing smart initializations of a parameter, and then why they consider linear RNM? Because during training you can view them as convolutions. So you can employ algorithm like fast Fourier transform to compute the state very efficiently, right? Which is very different from non-linear RNN, where you need to compute the state sequentially, right? So you could not use pairalizations for non-linear RNN. Whereas with linear RNN, you could use pairalizations, which will speed things out a lot faster, right? So so it could add a convolution during training, but during testing, during inference, you could basically, it works like RNN. So things are quite flexible here. So the idea of SSM is that you develop architectures based on linear RNN upon suitable initializations of the parameter A in particular. And then you apply nonlinear activations, and then so this is one block, and then you stack many blocks. So these are really lead RNNs, right? And then they've shown that these type of architectures are able to achieve really good performance on the long-range arena task, which is a benchmark task to test the long-range capability of sequence models such as transformers and other sequence models. So there are some like a bit of hype, a bit actually around SSMs. So what I want to stress here is that while SSM, they are really good for like the long range arena tasks, they might not be optimal for simpler tasks, right? Such as just predicting nonlinear dynamics. Because usually SSM, you will need like a very high number of trainable parameters. And for like smaller problems like SciML type problem, you might not need that, right? It really depends on the amount of data that you have. So for example, for nonlinear dynamics, we found that if we compare tau GRU with, so S4 is one particular type of SSM. So if we compare them with almost the same number of parameters, right, then tau GRU actually perform better. So there are different regimes where different models perform better than the others. So yeah. So another thing that I want to stress is that SSMs are typically deep RNN, they are deep architecture. So it's not really fair to compare this with our architectures tau GRU, which is just shallow RNN. Okay, so these are some comments just in case if anyone is interested in, so how tau GRU is compared with SSM. All right, so just to summarize, so our starting point is continuous time delay differential equations. And then from this, we basically derive a new architectures that we call tau GRU. The key feature of this is that we incorporate a weighted time delay feedback mechanism into the architectures. And the intuition behind this is that this should be able to lessening the vanishing gradient problem. So we also derive the gradient bound for this to understand why this is the case. And we show via experiments on a variety of different tasks that how tau GRU compare with other RNN architectures. And lastly, I want to make advertisement. So I'm just starting a new position at KTH, as I told you earlier. So currently I'm looking to recruit postdocs to work on projects at the interface of generative AI and sequence modeling. So feel free to help me to spread the works, or if you're interested yourself, talk to me about this. Thank you.